Okay, let's see if we can understand the basic specifications of a synchronous counter organized as usual as a finite state machine. This time the objective is the discussion of the functionality, the symbol that is represented in this picture, and then some features like the idea of up counting one digit information in BCD like this 0, 1, 2 and on up to 9 and then again 0, 1, 2 and etc etc. This wheel of numbers, 10 numbers. So we will see how it is possible to invent this chip, and we will add some extra features as well, like the count enable and terminal count inputs and outputs, so that we can go and change similar devices like this, making expandable counters. So we will be able to get a larger counter, for example 2, 3, 4, 5 BCD digit counters very well, using this device later on as a component. So guys, let me discuss with you a little bit the specifications of synchronous counters, okay? For example, the counter BCD one digit that has to be like this, you see? A symbol that has these special inputs, clear direct and clock, and then, for example, a control input, count enable, and another output that is like this, TC10, terminal count 10. So this is the terminal count, and I will explain the meaning of this terminal count, and this is the count enable. So let's discuss this way the specifications of you see, one digit BCD up counter. You may call that way up because it's counting up synchronous counter. You see, one digit BCD up counter, that is nothing but a synchronous device, you see, controlled by the clock signal. So the idea is that now every rising edge from this system clock, you have a new value, 0, 1, 2, 3, 4, 5. This is the idea of synchronous counters. Let's go counting up or down or whatever else, but this case, let's make it simple. Only one control input to stop counting or to allow the counter go on, and a terminal count that you will see that it's just a teeny pulse every time that you are at the state 9. So you see, you can start like this, imagining the number of inputs and outputs that will contain your entity, the name of the entity, counter BCD one digit at .bxd, the output queues and the like. So the functionality, is described by this function table, and everybody knows that the functionality is depending on the clock, so and the clear direct. So these signals are not necessary to be organized here in this function table because everybody knows the way they work. I mean, if count enable, yes, count enable maybe 1 and 0, you see? So let's decide what is going to be next in the code output, you see? So for example, if count enable is sampled to be 0 on the rising edge of the clock, remember that this is the meaning, be careful, this is not a level, you see, this is the value, the sampled value at the clock's rising edge. That is the idea, okay? In the same way, this is the future state, the next state to go, and now this is after the clock's rising edge. That is the idea, okay, of the future state in these standard canonical sequential systems that we are inventing already from P6 and on and on. Even the 1-bit flip-flops were invented like this, as asynchronous devices that has this mechanism related to the clock rising edges. So if This time, this machine, you see, it's like this. If count enable happens to be 0, the Q is kept the same, okay? Do nothing. Do nothing is the idea, or disable counting, you know? Or keep the same value. If the counter is generating now a 2, so after the rising edge you will still have the 2. But if you have a 1 in count enabled, what you like next is the current value plus 1, you know? And this is in modulo 10, you see, BCD. You see, binary code decimal, modulo 10. And the meaning of this is that the codes that you will get here is that way: 0, 1, 2, and then 9, 0, 1, and so on. And so that is the sequence. So when we talk about the 2, naturally is 0, 0, 1, 0. That's the idea. We have a binary combination, but a sequence of ones and zeros that means numbers, binary numbers from 0 to 9. So this is what you get in this counter. And plus means that it's counting up, you see? Plus 1 means that it's counting up counting. Later on, you will see that you can very well generate here another control that is up, down, L. So this is later. You know? Let's do one thing at a time. So this extra feature, that means reversibility in counting, may be added later as a new feature. So let's just start some way. This is the phase 1, a very simple counter. So, well, we have the job to define it completely and then go to the plan and then go to the lab and run the synthesis and the developing to the end. So this circuit is explained like that, using the symbol and the function table. But you know that what goes next here and is going to occupy the rest, you see, all the blackboard is, you know, the idea of the timing diagram. So because it's that important, you see, you have to know in time what happens, and to do that here is nothing but a timing diagram that you see is for generating several clocks and guessing what is going to be the output for every clock depending on the control inputs and everything else. So you see, you may have many clocks. So take your time, take a sheet of paper and do that idea, okay? Represent many clocks. Probably here you have 10 codes. So to run the full wheel of 10 states, you see, because in the end this is nothing but 10 states, you will need 10 clocks. And what goes next, as you know, you see, again, I have to insist on this, what goes next is the rising edge, because this is what is necessary to know very well. If the outputs, the coded outputs in BCD has to be changing, that change is only available, only permitted, only possible after the rising edge of the clock, if you let the system go counting. So that is the idea, okay? So this is why you have to take a sheet of paper and do this operation of marking in time, like this, the rising edge of every single pole. So this is what I mean, and this as well is the parameter that we call the period of the clock, which is nothing but 1 divided by the frequency of the clock. So you can have a clock 1 hour, 1 second, 1 microsecond, or 20 nanoseconds, doesn't matter, you see? That is a parameter, clock period. Then later on in VHDL is called clock period. The value that you will add as a constant to the test bench. So you see, then what? Well, there is another signal that you have to drive as an obligation to make it possible the system run, knowing what is exactly remembering, and this signal is clear direct. So you very well can imagine that at a given time, when you like, you drive this signal high and you keep it high for a while, and then you keep the signal down, and later on, if you like, you can keep the signal high again, but doesn't matter, okay? At least you have to to allow the system go running when low. So when high, you see, when at 1, when this level is assessed, you have to take care of another important time. This one here. You see, when clear direct goes high is when the system will initialize, reset. Okay, so now you can imagine that you are inputting some values for the count enable in time. So this is what you have to imagine. Count enable activity, for example, like this, and then here you stop counting for a while and then you continue counting. You see, something like this. Why not? It's up to you, the one who are structuring the values of this count enable. And finally, the outputs. So here is the queue. Okay, what is the queue at a given time? This is the purpose of the simulations. And these demonstrations, you see, we are just starting talking about this chip, so we have this idea. Let's imagine what is going to be the queue and the TC10 as well, the other output. So this is the idea, okay? So you see a full sheet of paper for thinking in advance what is going to happen in this circuit. As usual, as any other machine, the same that we did in the traffic light controller or the 16 key matrix keyboard. Anywhere else we did the same thing, okay? Or the button debouncer filter, and every time we have to do that to get a very good picture of what is going on. So you see what I'm telling you now, that before this clear direct level, you see this is a level high. Because of a level high, this assertion has precedence over anything else in this machine. So from now on, the Q that was not known, you see, was undetermined. So the output and the Q was not known, you see. This is unknown. You never know what is happening when you connect the power supply to the system, you see. You are switching on at t equals 0 the battery to the system, VCC, and now when you connect the battery, the system sets itself to some value of ones and zeros, but so it is undetermined. You know nothing about this initial value. But when you click clear direct, just driving a single pulse, now the machine is settled very well, so the Q goes down to 0. So at least meanwhile you have a 1, and up to the next rising edge. So you see this is the first rising edge of interest. Absolutely, that one here, the one after the clear direct assertion. You see, now from now on you do not have the CD, so from here you can start sampling, and meanwhile what you have here up to this point is a 0, okay, and TC is 0. That is the point, a 0 value and a 0 code, 0 0 0 0. So this is the starting value, because we have this idea, reset the machine, get a 0. Then what? Well, then you must pay attention absolutely to the value of the count enable that you are sampling. Okay, what is the meaning of this? Well, take another color if possible and do that idea of sampling. This is the value that you have here, a 1. So because you have a 1, you see now the counter is able to change to the number 1. And because you have a 1, you here are changing to the number 2. Because you have another 1 here in this third rising edge, the counter is generating the number 3. Remember, okay, when I say that you are, and because TC10, I have not said so, but you know, now it's my time to explain that TC10 is 1 when state 9, when 9, you see, TC10 is 1 when 9, and another condition, a logic AND. You see TC10 is high, is asserted when state is 9, not 8 or 5 or 2, but 9 is the last state. You see, this is the last state, the terminal state, the terminal count, or the last state, and you let the system go counting. This is the other condition that you have to take into account. So here you are letting the system go counting, but the states is the 0, the 1, the 2, the 3, but not the 9. So all these states, you see, the TC is kept low. So now you sample again another 1. So instead of the 3, you have the 4. But now what happens? You see, you are sampling a 0. Be careful with this. You see, the level 0 has started here. But you are not aware of the level in the control inputs. Okay? You are aware not of the level, but only about the value that you are sampling. And here, on the rising edge, this rising edge, you are sampling a 0. So now is when you just repeat the 4. This is the meaning of not letting the system count. You repeat the 4 even another time, because again, you sample a 0. So you see, the 4 is kept for all these 3 perfectly right clock periods. But now you see, it went high before the arriving of the rising edge of the clock, but now you sample a 1, so now again you have the possibility to switch to a 5. The current state plus 1, this is the idea of a counter. And then again another 1, so you switch to a 6, and then you switch to a 7, because you are sampling another 1. You see, this is the way, not take it easy, right? One clock at a time all the time. So the TC10 is all the time 0 for all these values. So now, you see, you have to take it easy, one clock at a time. Take it easy, because what goes next is like this, depends on the rising edge of the clock and the values that you are sampling. This time is simple because you are simply taking care of the value of a single input variable or signal. So you have a 1, so you now 8. And take it easy, you see, go marking the many more rising edges values that you need that way. Okay, go to the end if necessary, no problem. Go like this, marking the rising edges. Okay, take your time. So now 8, and another time you sample 1, so you now have a 9. And because you have a 9, TC10 goes high, especially because you are letting the system count. So this is a 9 now. So 9, and then what else? Because you are sampling again here, another 1, 0. And then a 1. And then what? Okay, then what? Well, another assertion of the clear direct. So look at this. This is synchronous. You see, the output changes only when you have the rising edge. But now you are going to force, as you did before, you see, here you are forcing, you see, in between the clocks, here you are forcing the situation. So you see, it was a 2, it had in mind to last until the next rising edge, but you see here you have another time a level 1. So this signal is assessed, it is asserted. So you see, it takes action immediately without waiting for this clock. So this clock is useless. You see, this is not used because it's overshaded, you see, by the presence of the clear direct value. So now the 2, you see, ends before time. You see, 1, 2, and the 2 is not the duration of the full period, but less than that. And then this means that you have a 0 up to this point. 0, you see, this is the idea of reset. Reset asynchronously. Okay? You have an asynchronous reset this time, because this is what you do with the signal high, and so on and so forth. So you see, and then because you are sampling again, this signal is not anymore asserted, and you have sampling a 1, you get a 1 that way. and then let's go to the end, 2, and so like this, you see? So anytime you like, you click and automatically it goes down to 0. So that is the idea of a synchronous counter. The simplest one, for example, a decade counter, a BCD counter, one digit counter that is working like this. You can keep the state if you like, or you can let the system go on. If you let the system go on, every time that the system is at 9, you have a pulse. So if the system is running continuously, you have one pulse every 10 pulses. So it's a kind of what? A frequency division, you see? It may look like this. You have a circuit that has an input clock and an output that is TC10. So now you may very well imagine the clock input, you see, a very high frequency if you like, and the TC10 output. This is the clock input and this is the TC10 output. And what is this? You see a pulse, and then later on another pulse, and later on another pulse. So this is another frequency here. This is the clock period, you see, T clock. So, and this is the period of the TC10. So what? Well, it is very simple. In some way, the period of the TC10 signal is 10 times the period of the clock. So in some way, you may very well imagine here 1 divided by n, in a way that you see the frequency of the TC10 is just 1 divided by n, the frequency of the clock. So that is the idea that you've got here with these pulses. A kind of a frequency divider, a very convenient circuit that we will use a lot of times from now on. This is a frequency divider circuit. Okay. In some way you forget about the code doesn't matter, but if you pay attention only to the TC10, this is what you've got. A periodical signal, and this is only if count enable is kept high all the time. You see, if you keep high all the time count enable, this is what you get. A periodical signal that has a frequency 10 times smaller than the one that you had in the clock. A divider by 10 or a divider by 12, in generally, this is the ratio in which the frequencies divide. You see, a natural number. It may be 2, 6, 7, any number indeed. That is the point of a frequency divider. So we will retake the circuit later on for structuring a circuit that is called clock generator, okay? But now it's just an idea that we get here, just keeping an eye on what we get if we represent in time TC10. Because look at this, if now, attending to the functionality of this TC10, you see, look at this, if now my count enable, this is the advantage of using a whiteboard that you can erase very easy. If now I do this, look at this, the system works. You have this pattern repeated many times, but later you disable count enable, but just for a brief period of time. If you do that, you see, if you do that, what happens? Well, you have a 9. So the Q is the 9, but count enable goes low. You see here, you have a 0 level. Okay, be aware of that when I talk about digital level and digital value sampled at the rising edge of the clock. So you see, when 1 here, you see, means a level high. Okay, so TC10 is sensitive to the input level. So this means that you see, now you can attach here another vertical cursor to represent what is going to happen. You see, you can generate another vertical cursor just to fix this level 0, and now this means that you have to modify accordingly the TC10, not the Q but the TC10. Yes, you see, so you can say that the TC10 is sensitive to, you see, count enable. So when count enable is 0, all right, it goes like this. You know, that is the kind of a discussion that is associated to this finite state machine, a counter. So what goes next is the planning of this machine. What is that is going to be inside of this entity? Well, so what I'm proposing you is up to 3 different plans. You will see a plan X, that is like in physics, you know, a standard finite state machine. Plan Y, which is slightly modified and in some way better. And then we will invent as well the counter as if you can use internal components inside, okay? Like if it is in plan C2. So that goes next. The same specifications repeated, photocopied 3 times because you have 3 projects in mind. 3 different circuits because you are planning 3 different architectures for, well, all the time finite state machines if you like, but slightly different one to the other. Okay, so that is what goes next, because when you have the specifications and the plan, you can go to the lab because the plan, you know, is transferred to a VHDL file, and what goes next is just running the synthesis tool and the testing applications to check that everything that you have in mind, like this, it is a good idea to go and test if it is true. You see, you have to, because it is that special that when the project ends and you have a circuit implemented into a fabric of a programmable logic device, you like to test, especially if this thing goes and if the outputs are synchronous and attached to every single rising edge and etc etc. Okay, so this is what is a kind of initial discussion of the counter.